Hi, my name is Reagan Miller, and my poster is entitled Fluorescent Chemosensing Molecules and Materials for Gas Phase Ion Detection. The International Physics Collaboration NEXT is interested in observing the decay of xenon into its daughter ion barium 2 for the investigation of the neutrinoless double beta decay. They do this by utilizing a time projection chamber which can drift negative and positive charges in opposite directions. Chemistry is included in this project through the NEXT Bold program, which designs fluorescent molecules to sense barium 2. Our ultimate goal is to design highly selective molecules which can be tied to transparent substrates in order to have fluorescent turn-on when exposed to barium at the gas-solid interface. The molecule of interest I'll be talking about today is called spiropyran. This molecule is unique as it behaves as a photoswitch, meaning there's a closed, non-fluorescent spiropyran form and an open fluorescent myrocyanin form when exposed to UV light, acid, and most interestingly, metal cations when synthesized with a binding domain. Making these molecules is modular and highly variable, but in this example, we utilize an indolene left-hand side reacted with a salicylaldehyde derivative on the right hand in ethanol, resulting in a chloromethyl spiropyran. Next, the substitution of a monoaza 18 crown 6 ether, which is sensitive towards barium 2 metal cations. This step, while seemingly easy, is extremely challenging due to issues with purification. This molecule is interesting because the closed and open forms have significantly different retention factors in normal phase column chromatography. And more so, the open forms can exist in multiple different isomers, which also have different retention factors. When attempts towards purification of these molecules have been done, normal phase silica, with its lightly acidic nature, causes the opening of the spiropyran closed form into the open form, which is highly fluorescent and has up to 6 different isomers. To limit this issue, we attempted purification with reverse phase silica, which does not have the acidity problem as normal phase silica. However, we had issues with the molecule getting stuck onto this phase. We also tried basic alumina to avoid the acidic problem. However, the molecule had virtually no separation in multiple different solvent fronts. We also attempted various recrystallization and crashing out methods in both polar and nonpolar solvents. We thought that light could be causing problems since these molecules are highly sensitive to light, and we also tried all of these conditions in the dark. However, none of these resulted in clean product. We are now looking towards a slightly different synthetic pathway which might aid in purification issues. Once we've successfully made this molecule, we will be able to tie it to a glass substrate utilizing an Aptas linkage. We start from plasma cleaned bare glass, which activates the silanols present on the glass surface. After the silanols are active, we will utilize a developed room temperature chemical vapor deposition method to attach Aptas onto the surface. Once we have a monolayer of Aptas that is established through chemical vapor deposition, we will do liquid phase deposition of spacers and fluorophores in order to create our final substrate, which should be able to sense barium 2 In the meantime, other simpler derivatives which do not have metal sensitive binding domains have been synthesized and their photophysics have been explored. Seen here is the photoswitching ability after exposure to UV light and the return to the closed form after white light exposure. You also can see the wildly different color change from the closed spiropyran form, which is seen here in yellow, to the open myrocyanin form, which can be seen as a dark purple. With increasing amounts of time under UV light, we can see an increase in its fluorescent nature. After being exposed to white light for 10 minutes, we see a return to the ground non-fluorescent state. On top of this, the photoswitching ability can be seen after 15 minutes of UV exposure after being turned back off in a return to this fluorescent state. An alternative synthetic pathway is also proposed, which allows for left-handed functionality with the binding domain crown ether. The final step of this synthetic pathway is purified by crashing the molecule out of water, which should aid in solving our challenges related to purification by eliminating the need for column chromatography. This project is done in collaboration with the Ben Jones Group here at UTA and the international collaboration of NEXT, and we are funded by the NSF and the Welch Foundation. Thank you so much for your time.